I'd like to thank Rafael for the invitation and all the talks that I've been able to follow. They were excellent. Very good for us to update ourselves and to get better in everything we do. So, the goal for my presentation today is not only to show the system that I've developed, but also to give you an overview on blockchain and how it can be useful for you. So, based on that, I extended my presentation to try to cover data connected to blockchain and also to present you with a solution that is a blockchain-based cooperative network solution. So when we think about solutions and attacks, this is a large problem, especially when we think about large-scale attacks. There are no defenses able to contain the large-scale attacks that we've seen both this year and last year. And this is my agenda. And I'll start with the motivation and thinking about denial of service attacks. So, as already mentioned by the speakers today and by the speaker yesterday, most of these attacks are on IoT devices because they are usually not very safe and they cannot be safe. We're talking about refrigerators, small devices, sensors that are restricted in terms of hardware, and they are very easy to be attacked by botnets, sorry. So I can show you the code. Just have to maximize it. So you have here the Mirai code. This is available online. It's been available online for many years. And what's going on today is script kits that get these codes and change them, make new versions, and launch new attacks. This is a stock Mirai version. As Eder said, people who make these tools, they are the real hackers. It's a robust tool, well developed, and I just want to show you a scanner, which is how you can scan a network looking for standard passwords, and based on this user and password, the standard one, Mirai was able to get many routers from Deutsche Telekom and cause a harmful attack in the end of 2016. Coming back to my presentation, so we have the attacks that are growing in terms of amount, scale, with the amount of devices. It's easy to learn how to use these tools that are already available. There are tutorials on YouTube that teach how to use it, and commonly there are 13, 14-year-old children using these things, checking on YouTube how to use them. Of course, they're caught because you don't need a PhD to execute that, but if you're not careful, you get caught. And that's what happens. And it's really difficult to get those that know how to do it properly. So you can be a victim of this type of attack. This is another Mirai-based attack that happened in 2016. And part of the traffic was DP traffic with DNS attack as well. with the traffic amplification. And the services that went down were Twitter, Netflix, GitHub, and other companies that use DNS services. These are other examples. We update the slides with new attacks. And a new one that I can draw your attention to is Memcached Attacks. This is a tool. You can put a cache distributed into your server, and instead of having two servers with 64 K of cache, you have 128 of cache that you can use in both servers. But then there is an attack vector that can be used for reflection attacks. This happened in April this year. Akamai was able to mitigate a 1.3 tera attack based on this tool used by many services, and the checking is usually not well done. Based on that, there's a scenario, and the current centralized defense systems, they are cloud-based or in-house, and they're not able to prevent these large-scale attacks. If there is terabit traffic, they crash the system very easily. So in research, we've been talking a lot, and this is what I do in the Missouri University, is trying to develop a collaborative tool so that there can be different systems helping one another because the attacks are getting more coordinated and distributed. So the natural thing is to have a tool so that defense can be coordinated and distributed, thus reducing detection and mitigation burden, and also extending mitigation capacities. So different attack detection mechanisms in different systems and a way to combine them. And what we see is that in theory, it seems really nice. Let's get the defense of different systems together, but there are many challenges. That's not something new. Since the end of the 90s, there are papers proposing overlay networks so that you can coordinate defense, but there are many challenges.
So I tried to list these problems in different scales. So we have, on the technical side, we have heterogeneous networks and systems. The TIM network works within as a different underlying infrastructure from Vivo and so on. So it's very difficult to have a protocol overlay to talk to both systems easily. So it's necessary to have some kind of platform or standard platform so that these systems can talk to each other. On the economic side, we need incentives to share the infrastructure. On the one hand, you have a defense team and a team of experts who are responsible for monitoring and managing a defense infrastructure. But not only that, the investment for equipment and maintenance of this equipment should also be considered. If you have a domain that is a constant target of attacks and you need collaborative defense, there's a cost behind this. So any type of mechanism for cooperative defense needs to be very comprehensive and include something to contain something that is able to handle this economical aspect. Another important aspect is the social aspect. Here we're talking about reputation and trust. The image may be of a domain may be the most important asset for a provider, and any information leak within this collaborative network may represent a problem with serious consequences. So everything needs to be uh, approached. And the fourth aspect is compliance, because there are different regulations that need to be complied with in different regions, both in terms of the states and federal government. So the question we have here is, how can blockchain help in this scenario? So here I'm just going to give you an overview of blockchain, and then I'll explain how blockchain may help here in this scenario. So blockchain in a nutshell, here we have a definition that it's a decentralized, distributed, and public digital system. It's not a trusted third party that is responsible for blockchain. It's a distributed system where all have the view of data within the blockchain. This is public and it's unchangeable, it's immutable. So basically, blockchain is the structure here that everybody knows. It's and you need a consensus mechanism to ensure that all the players in the blockchain have the same view of the data. So every time a block is created, for example, this last block here, you need to ensure that all members, all parts of the blockchain have the same block. And here, you don't create a fork or a side chain that can be created over here. So you can create one blockchain up here and then a side chain down. So, and that creates a problem, which is the double spending. And so I'm also going to try to dissociate blockchain from cryptocurrency, which is an application for blockchain. So here we're talking about this type of infrastructure, a blockchain where you need a consensus mechanism to prevent forks and sidechains. Another important component when we talk about blockchain are the smart contracts. This is an idea presented in 1994 by Nick Szabo. And at the time, there was no ideal infrastructure for smart contracts to have the same meaning it bears today. So the smart contract needs to be self-executing and self-enforcing. So it should be self-enforcing. And with blockchain, this is possible. And in this case, we have a very simple contract example, a hello contract, where we say here that every time we call this function, the get hello, we'll receive a hello world message. It's very simple. And here we simply create this and put this in a smart contract, call a transaction to store this contract in the blockchain. And once this is stored, you get a hash back, which is the identifier to access this contract. So anyone since blockchain is public, or anyone who has this ID can look at this, call this function and see the hello world. This is very basics. Bitcoin, for example, has a smart contract that is basically, I want to send funds to someone else. So the contract is very simple in that sense. However, there is also the possibility or the flexibility of storing a contract that matches your purpose. For example, here in the smart world for collaborative events, I use hello world to sign the address. So you can use blockchain in this way. And how does this work? We have here this example considering Alice and Bob as the users, Dave and Eve are the miners, and the standard blockchain in the middle. Considering this is a distributed system, or in other words, you have these actors in different networks, and Alice wants to send information to the smart contract, to Bob's smart contract. What happens after this is that once this information is submitted to the blockchain, all transactions are in this transaction pool. And here, It's just waiting to be mined and added to the blockchain. So you have Dave and Eve over here waiting to dispute the transaction in the transaction pool to mine the block. So the next step would be to use a consensus algorithm to prevent the issue I was talking about, the creation of forks. We don't want Dave to generate blocks in a parallel chain, and we don't want Eve to do any of that either. So you have to use an algorithm to ensure that everyone will create blocks in the same chain. So here you have different choices, different alternatives for consensus algorithms that are not based on proof of work that is used for Bitcoin, that are, for example, proof of stake, which will inform how much money has been invested in the network. And this ensures the ability to generate, to create a block, to understand the stake, and authority to create a block. And the other algorithm is just proof of authority, which could be Dave can be considered one authority, Eve could be another authority, and they can create blocks in a round robin. For example, Dave creates a block when it's available in the transaction pool, or Eve does it. But focusing on the proof of work, sorry, my image did not, my graphics did not work. But you need to solve a mathematical problem. So once you have the transaction pool that is ready for mining, Dave and Eve needs to solve a mathematical problem. You need to find the zeros in the hash based on a random number to adjust the difficulty of mining in the blockchain. And this requires a lot of computer resources. And in this case, whoever has the most resources will win. And depending on the algorithm, this could take up to 15 minutes, which is the average time to create a block, around 14 to 15 minutes. So here we consider that Eve found the hash, so she'll be able to create a block. And because she spent or invested, she will receive incentives, which is her reward, the transaction fee as a reward. And from that point, the new block is added and propagated to the network. So Bob can now read the information that was not stored by Alice, that was stored in that Alice stored in Bob's smart contract. So this is an overview of how blockchain works. Of course, there are many more details in each of these consensus mechanisms. And you also have different blockchains, not only for Bitcoin. We have Ethereum, Hyperledgers from IBM. So there are different implementations with different properties. So there's some flexibility. But maybe one of the things that we see the most, maybe I can say that Switzerland has a very strong culture, has a very strong blockchain culture, because many banks in the finance industry is very strong, and banks are the main interested parties in explore this. And we look at all the environment and several startups using ideas that sometimes make sense, sometimes they don't. And based on this, our colleagues from the University of Zurich proposed this methodology that basically guides the use of a blockchain. And it works as a blue filter. It will tell you if you should or should not use a blockchain. So the first step here, you have to store state. So the first two steps are very simple. If you don't, so you don't need blockchain. Are there multiple writers? If the answer is no, then you don't need to use a blockchain. And the third step, do you need to use a trusted third party? Is there a trusted third party that you can rely on? If so, then there's no sense in using blockchain. You can use a traditional database, and this is a technology that has been available for a long time, much safer and much more reliable. And in the case here, when you don't have a TTP, a trusted third party, so you take another step and you have all the writers and all the people who can actually submit information to the blockchain. And this step will define the type of blockchain that can be used. If you don't know all the people who can submit information to the blockchain, in the case here, we have the permissionless blockchain, in other words, a totally public blockchain. And this is where you find all the cryptocurrencies available in the market. Anyone can create an account, can have funds, and send funds to anyone else who also has an account. So in the case here, the Academy defines this as the classical blockchain. But there are other types of blockchains, not only public, based on proof of work. So going back to the previous question, are all the writers known? No. So you have all the writers. Are they all trusted? If you say yes, once again, you don't need to use a blockchain. If these writers are not trusted, you would need to understand if you have verifiability. And in this case, we need to review the outcome of the transactions, quote unquote, the public transactions, not public for all the writers, but public within a specific group of writers. If yes, then you have a public permissioned blockchain, which is a blockchain that everyone can read, but not everyone can write in. This could be useful in cases where you need to have proof of identity of something. You might have certain entities that are responsible for authenticating and creating a hash that can be written in the blockchain, and everyone can read that hash to ensure if that ID is actually generated by an identity, recognized identity provider. For public verifiability, it's not necessary. So in this case, you have a private permissioned blockchain, which is a blockchain that is closed off to a specific group of entities where not all have access, and only those who are selected may write in it. But that in itself does not ensure the need for a blockchain, because you also need to consider the transparency aspect, transparency and reliability and confidentiality, especially in the security scope. Confidentiality is something extremely important that needs to be considered. So we have this trade-off in the blockchain. Blockchain is transparent to a specific audience, and if you need and if you're working in a security setting, you might need confidentiality. So there are a number of aspects that need to be considered before using blockchain. Here, what I did was to map the application that I'm proposing. I'm proposing a collaborative system based on blockchain. So it would be fair to review if blockchain makes sense or not. In the case, if you need to store states, then the idea is to signal an attack where you can verify who signaled that attack so that you can actually pay a fee or an incentive. A cooperative system requires more than one entity. And this is a question that is very important in the blockchain adoption process. And it was very difficult because there isn't always a trusted third party that you that you can trust. And if you're talking about a collaborative system against attacks, it's very difficult. It's unlikely that one single entity can be trusted by all the other entities. So in this case, blockchain is a transparent environment with no centralizing entity, and everything that is written is recorded and is open to the audience who has access to the blockchain. And in this case, the question would be, are all the writers known? Yes, because when you're talking about an alliance, of course, you're going to choose members who are aligned with the goals of the alliance, which is cooperation around around cooperative defense. If you trust all the writers, you would need to you would need verifiability, or in other words, since there are incentives involved, and you need to pay for these incentives to cover expenses for mitigation. So we need the verifiability aspect here in this case. And public verifiability here is not necessary because we're talking about the public image of an internet provider is a very important asset, and in this case, this cannot be open to the general public. So this blockchain that is being proposed is closed to a consortium where only certain members can read and write in the blockchain. And based on that, we chose Ethereum, which is the blockchain that allows this flexibility for smart contracts to be stored. So the important aspect here is not only understanding the basic the basics of blockchain, but also understanding how blockchains can be useful for your security applications. Many times you'll get your answers will be no, because this is what we've seen in practice, and in many cases blockchains are not necessary. And it's very important to understand many of these steps, not only those steps, but also the trade offs in terms of confidentiality and transparency, privacy, performance as well, is something that needs to be considered. So these are all the aspects that need to be considered to adopt a blockchain or not.
So, how can the blockchain help? We are assuming that there is an attack to the autonomous system, and so this autonomous system can be in place with an in-house defense system or a cloud-based defense system. If these systems are not enough to mitigate the attack, there can be the preparation of an attack report, and this information can be submitted to the blockchain. And based on that, once the entire block process is done, the other participants can receive these smart contract. Well, actually, this information that an attack is going on. Based on that, they can make local decisions based on their own policies or the condition of the network to know if they help or not. So, assuming that there was cooperation, the traffic flows normally again. So, presenting my specific solution, we have the blockchain signaling system, which signals an attack. This system was proposed and it's the core component, and it can be used for in a VM. It's also called pollen. So it's an API that communicates with the blockchain and with the stalk. So the stalk is the network management system. and an API hash was built to communicate with the system. The Poland is it's this other database where information can be collected for to do a cooperation defense request. Based on that, using the IPFS technology, which is an interplanetary filing system, for this case, we're using it to store the reports, and just a hash is signaled in the blockchain because a blockchain it's naturally constrained in terms of storage space. So you cannot store an entire report. When you think about a large scale attack, so the idea of this technology is to combine different systems. So if you have a cloud-based DDoS defense system, I use the Cloudflare example. There can be also an in-house defense system, or if none of them is enough, there's another option which is using a collaborative system. Based on that, we've proposed a mitigation protocol considering that T is a target and M a mitigator. So the target can request a mitigation. The mitigator can accept it or not. And if the target, before starting the service, the target can give up in case the attack has already been mitigated by the in-house or cloud-based defense. So they can give up the request before starting. If the mitigator accepts the agreement, it needs, there's a deadline. We call it service deadline. So they need to do the mitigation service and provide a proof that the mitigation was done. So there's no solution currently for you to give or offer a proof of mitigation. There are different possibilities with regards to the validation of the service once it's done. So it can be you can be dissatisfied about the service, you can be satisfied, and then you give a positive assessment, and the mitigator can rate also the behavior of the person who asked for the service. And if everything occurs okay, then the fund that is deposit on the blockchain is paid for the person who did the service. I'll speed up a bit with regards to configuration and operation. These are the technical aspects of the solution. You need to configure. These are the intervals that you're going to ask for information from the blockchain. These are the networks that are managed. And operation, which is a team that is able to make decisions if it will be necessary to report the attack on the blockchain or ask for a collaboration defense, or for mitigators they can ask or they can accept for a mitigation proposal or request. So the first prototype was implemented in DM. It didn't work. So there different hosts and service providers had to be implemented, and sending traffic was not a good solution. The second prototype was implementing the system that we have over there. So for the we would have some lights blinking, white lights. We have the red ones, so these are challenges. These are the bots. These are independent domains, and we have the networks using a switch. that is SDN. And here two controllers to check for the operation of the cluster. Recently, we completed a global assessment of the system. Several, 8 instances were deployed, and we wanted to see how the system behaved to transfer the files. The results don't have formal validity, but they can be an indicator to see how the system behaves. We have here the time in seconds. I'm not talking about the time of propagation of the block, so you could add another 5 seconds. And in the worst case scenario, almost 18 seconds were necessary to spread the list of addresses of attackers. So let's go to the demonstration. The scheme is being used, and basically what I'll try to do is generate traffic to attack the victim. And once the attack is detected, then this information will be signaled in the blockchain and the other domains will attack. So let's go to the demonstration. There's some blinking red lights, which is not very good, but that's what we're here for, right? Right, so what I've done, right, so on the top we have the blockchain generating blocks. So here we have the front end. You can see that every 5 seconds a block is generated. And here we have the monitoring for the traffic. What I'll do now is generating traffic. So the command is ready. I'm gonna send this command generating 20 mega of traffic. We see that the LEDs turn on and we can see that the victim starts receiving traffic. So I'll change now for the Grafana vision. So here you have an idea of what's going on. We can see the third system being overloaded. And when the attack is mitigated, the inbound traffic will go to 0. So a cooldown system is set up, and then the attack goes on and out, in and out, just for the presentation. So it's basically it. So I'd like to show you. These are the blocked addresses. You can do the report, encrypt it, put it on the blockchain, and the other systems can receive this information. So coming back to the presentation. So that's not the slide that we want. So to close, blockchain can be used as a Swiss Army knife. It's not going to solve all the problems. I'm the second year of my PhD, and what I can see is that it can help solve some of the technical problems and social problems, providing more facility for that. But there are other challenges, which is transparency, the relationship between transparency and confidentiality, how much open a provider would be to provide this information to blockchain. We don't know that. For research, my task is to provide a solution first, and so then I can check how this can be adopted in the practical standpoint. And GDPR, blockchain is immutable. Everything that is stored there cannot be moved. And in the most companies today, they don't know or don't care with blockchain, unfortunately. And most of them do not accept a hash representing a data to be stored in a blockchain. We have a project with a Swiss company that monitors supply chain. They call it cold chain supply chain for the pharmaceutical industry, and many companies do not accept for you to store a hash representing a list of measuring of the temperature during transportation. So this is still a problem. We don't know how to adjust the solution for the current regulation in Europe and other regulations. So this is what I wanted to share with you. Thank you.